Hey guys! Welcome back to the laboratory. In this video, we are looking at dynamic equilibrium. By the end of this video, you should be able to define the term reversible reaction, describe how ammonia is produced in the Haber process, and explain how changes in temperature, pressure, and concentration affect equilibrium. So, let's go! Most chemical reactions can only occur in the forwards direction. In the forwards direction, the reactants react to form the products. The general equation for these types of reaction would look something like this. In these written equations, this arrow is used to indicate that the reaction only takes place in the forwards direction. In a reversible reaction, the reaction can take place in both the forwards and backwards direction. In the forwards reaction, the reactants will react to form the products, and in the backwards reaction, these products can break back down into the reactants. The general equation for a reversible reaction would look something like this. In place of the forwards arrow, we use a double arrow to show that the forwards and backwards reactions are taking place at the same time. Let's look at this concept in practice. In the forwards reaction, reactants A and B react to form product C. In the backwards reaction, product C breaks back down into reactants A and B. At the start of the reaction, there is a large concentration of reactants A and B, and so the forwards reaction occurs very quickly. As the reaction progresses, the concentration of reactants A and B decreases, and the concentration of product C increases. At this stage, we see a decrease in the speed of the forwards reaction and an increase in the speed of the backwards reaction. After a while, the speed of the forwards and backwards reactions will even out. At this stage, the reaction has reached dynamic equilibrium. Dynamic equilibrium is only observed during reversible reactions. This occurs when the forwards and backwards reactions are happening at the same rate and the concentration of the reactants and the products are the same. The term itself describes the process, with dynamic indicating that the reactions are constantly happening, and equilibrium indicating that there is a balance. Do note that dynamic equilibrium can only be achieved in a closed system. In a closed system, no reactants and products can escape, particularly those that are in gaseous form. However, in an open system, the reactants and products can escape, and so dynamic equilibrium cannot be achieved here. The manufacture of ammonia involves a reversible reaction between nitrogen, which is obtained from the air, and hydrogen, which is obtained from natural gas. Ammonia is an important industrial product used to make the fertilizers needed for healthy growth in plants. There are a number of specific conditions that must be met in order to favor the forwards reaction and yield the maximum amount of ammonia from the process. Firstly, the reaction must take place at a temperature of 450 degrees Celsius, at a pressure of 200 atmospheres, and with the use of an ion catalyst to speed up the entire process. Changes to the conditions of a reversible reaction will cause a shift in the equilibrium of that reaction. In general, when a condition is changed, the equilibrium will shift in the direction that counters the change to the system. For example, in the reversible reaction between nitrogen and hydrogen to form ammonia, the forwards reaction is exothermic, meaning it releases heat into the surroundings, and the backwards reaction is endothermic, meaning it absorbs heat from the surroundings. When the temperature of the reaction is increased, the equilibrium will shift in the endothermic direction, therefore increasing the production of nitrogen and hydrogen and absorbing more heat from the surroundings. However, if the temperature of the reaction were decreased, the equilibrium of the reaction will shift in the exothermic direction, therefore producing more ammonia and increasing the amount of heat released into the surroundings. Similar changes are observed when the gas pressures of the reaction are changed. When the gas pressures in the system are increased, the equilibrium of the reaction will shift in a direction that produces fewer gas molecules. During the Haber process, this would mean a shift in the forwards reaction, therefore producing more ammonia. This explains why the Haber process is carried out under such high pressures. So, what do you think would happen if the gas pressure of the reaction were decreased? You guessed it, the equilibrium will shift in the direction that produces more gas molecules. Changes to the concentration of reactants and products will also cause a shift in the equilibrium of a reversible reaction. When the concentration of a substance is increased, the equilibrium will shift in the direction that will use up more of the substance that was added. For example, if more nitrogen and hydrogen are added to the system during the Haber process, the equilibrium will shift to favour the forward reaction, therefore producing more ammonia and using up the nitrogen and hydrogen that were added. However, if the concentration of a substance were decreased, the equilibrium will shift in the direction that forms more of the substance that has been removed. If nitrogen and hydrogen were removed from the system during the Haber process, the equilibrium will shift to favour the backwards reaction, whereby ammonia will break back down into nitrogen and hydrogen. Here's an example of a past paper question that I'd like for you to attempt to test your understanding of the content covered in this video. Pause the video and take your time to work it through. Press play once you're ready to check your answers. Hydrogen reacts with iodine to form hydrogen iodide. Iodine gas is purple and hydrogen iodide gas is colourless. Hydrogen and iodine are placed in a sealed container. The container is left until equilibrium is reached. The conditions are changed, favouring the forward reaction. Explain what you would see. A lot of important information has been given to you in this question, and it's important that you use it all to your advantage. To begin with, the chemical equation provided in the question indicates to us that the reaction between hydrogen and iodine to form hydrogen iodide is a reversible reaction. In the forward reaction, hydrogen and iodine react to form hydrogen iodide, and in the backwards reaction, hydrogen iodide breaks back down into hydrogen and iodine. The reactants, hydrogen and iodine, are placed into a sealed container. This information is important as it tells us that the reaction is taking place in a closed system. Therefore, none of the reactants or products can escape. The container is left until equilibrium is reached. At this stage, both reactions are taking place at the same time, but the amount of reactants and products is equal. We are told that iodine gas is purple and hydrogen iodide is colourless, so at equilibrium there is an equal mixture of the two in the container. The conditions of the reaction are then changed to favour the forward reaction. Therefore, more hydrogen iodide will be formed. We need to explain what we will see. Now, with any explain question, you'll need to make a point and then follow that point up with an explanation. This also explains why the answer to the question is worth 2 marks. The first mark for this question is awarded for stating that the gases in the container will become less purple or fade. And your second mark is awarded for explaining that this is because there will be less iodine in the container. So, how did you do on this question? Let me know in the comment section below. Anyway, that's it for this video, guys. Thank you for joining me in the laboratory. Please leave a like on this video if you found it useful, and don't forget to subscribe to the channel so that you don't miss another one. See you soon!